Okay. Hello, everyone. Welcome to the presentation of our work for PCS 2021. My name is Zhenzhong Tu from UT Austin. Today, I'm going to introduce our work collaborating with the YouTube Media Algorithms team titled Efficient User-Generated Video Quality Prediction. So here is the overview of this talk. We'll first talk about the background about the user-generated content and video quality assessment with a brief introduction of their applications. Then we'll introduce some related works. The proposed blind VQA method is also introduced in the next section, followed by the experiments and conclusions. So what are user-generated content? By its name, user-generated content are those uploaded by users and creators. So let's take a look at some examples from YouTube. So loosely speaking, UGC videos may include almost every video you saw on social media platforms. We are interested in video quality. So regarding video quality, there are several attributes of UGC that differentiate from traditional video quality assessment. So firstly, UGC videos have various quality ranging from very bad to very good. And secondly, they also contain a variety of content types, as we can say in this demo, such as gaming, vlog, animation, sports, TV shows, etc. Last and most importantly, unlike high-quality streaming video scenarios where the distortions largely arise from compression, UGC videos commonly contain other types of distortions that occur during acquisition by the amateur videographers they are usually intermixed. So these distortions may include various types of compression, blur, over-underexposure, low light, noise, shake, resolution, etc. Therefore, blind video quality assessment of UGC videos is a very challenging yet unsolved problem. So the definition of UGC-VQA problem is very simple. And so it's just a regression problem that given any social media video X, we are blindly predicting its perceptual quality Y, where the source UGC video has unknown and the intermixed distortions, as we have just discussed before, and Y is a numerical quality score representing the overall perceptual quality. So these scores are usually collected by conducting a large-scale subjective study. So the industry such as YouTube and Facebook has a lot of interest in this problem because they wanted to assess the quality of videos uploaded to social media such that they can further deploy smart pre-processing techniques based on their input video quality. And accordingly, design a better compression paradigms for these UGC videos. Another very important application of UGC-VQA is the injection to streaming services such as Twitch to help monitor the quality of the experience. So there are a lot of related works for these blind VQA models. We have collected some here, including the natural science statistics-based methods like Breeze, Nike, GMlog, Freaky, High-Grade, and they also video blinds, TL, VQM, Videoval, etc. And there are also other types such as the dictionary learning-based methods like Cornea, HOSA, and also a few recent deep learning-based methods like Concept and the PAC2PIC. For a video quality model, efficiency is very important. Here we tabulated the complexity comparison of these VQA models from our previous studies. So the current state-of-the-art model, Videoval, is compact, is top performing among these test beds, but as the table indicates, it is not very efficient. So the reason could be that Videoval is built on top of other models. Even though we have tried our best to exclude the expensive features, the leftovers are still not very good enough. So another issue is that we use the dense frame sampling rate inspired by the previous method, but it may not be that necessary to do such a dense frame sampling. So This is our motivation of this work. So with these motivations in mind, we built another model called the RAPIQUE. So the RAPIQUE and Accurate Video Quality Evaluator to address the trade-off between the performance and speed. We want this new model to be as efficient as it can. So here we show the block diagram of the RAPIQUE. It may be a little bit complicated, so let's parse it step by step. So in this slide, we give a high-level overview of RAPIQUE, or to say a summary of our contributions. So firstly, RAPIQUE is a first of its kind blind VQA model that combines NSS and CNN features together. And within these NSS features, we built a new spatial NSS module that is an order of magnitude faster than VideoVol, but with similar performance. We also designed the first general temporal statistics model beyond simple frame differences for analyzing emotion-intensive videos. To make it efficient enough, we apply the ResNet 50 on the downscaled frames when extracting these high-level semantic features. We assume that our proposed NSS features are sufficient to capturing this technical quality, and we only leverage the same features to capture additional high-level features. So we don't need to apply them on the high-resolution frame. So lastly, aggressive frame sampling rate is used to improve the efficiency while keeping the performance state-of-the-art. We consider this last point as a significant engineering contribution. So we want RAPIQUE to be modularized. So we started with building a very basic feature extractor, which may also be used in other future models. But we use basic statistical features from local variances, like from generous Gaussian distributions, and also from the asymmetric generic Gaussians. The 34-dimensional NSS feature extractor is built as follows. First, the mean and variance parameters are extracted from the local variance of the image. Then we extract two GGD parameters from the mean, subtracted, and contrast normalized map. So these are very common features that was used in all the previous VQA models. Inspired by the BRISC and the high-grade model, we also extract the MSCN pair products and log derivatives to model high-order statistics. So this table summarizes this basic 34 feature extractor we have built. And we assume that these features are capable of capturing a variety of statistics, and thus we can apply it on various feature transforms and color spaces, like as we did here, like we apply it to Y and the gradient magnitude, Laplacian of Gaussian, difference of Gaussian, and also several color spaces like LAB, O1, O2, O3, LMS with their gradient domains. So this page concludes the spatial module of the RAPIQUE model. So for the temporal part, we have built the first general temporal bandpass statistics model for blind VQA. So inspired by the reference paper here, we applied a 1D Haar filter temporally to extract the temporal wavelet responses of these frames, as shown in the second row of the figure. And for subband 1 to 7, we again apply our NSS34 extractor, obtaining a total of 476 features. Note that we apply this feature extractor in 2 scales, so the feature will double, then yielding a total of 476 features. Since we are the first to take this approach for blind VQA, we only try the simplest bandpass filtering, that is the Haar basis, and we observe that this already performs very well. We'll leave other advanced bandpass operations to future works. So let's get back to the diagram again. So in total, we have around 4,000 features in RAPIQUE. wherein the top red box extracts the 680 spatial features. And we also apply the temporal variance pooling of these spatial features to get another 680 dimensional features, which has been shown effective in previous works. So we also apply this trick. So in the middle box, the 476 temporal features are extracted. And in the bottom red box, we extract the 2000 ResNet 50 features from a resized frame. And they are all concatenated together for training a single regressor. Here we use a simple SVR for training. Note that we use a very sparse sampling because we think that both the content and distortions in space and time are kind of redundant, and we can fully make use of this redundancy to improve our model efficiency. And we believe that our use of the rich features can somehow compensate for the aggressive and the sparse temporal frame sampling. So how good is RAPIQUE? We may observe from this big table that RAPIQUE achieves quite good results across all the tested dataset. Note that in the combined dataset, VDeval is built by a supervised feature selection on the combined dataset. So it is quite promising that RAPIQUE, which was built from scratch, can beat the VDeval on the combined dataset. And we also observe that RAPIQUE can benefit from larger dataset training because it just contains a lot of features, and we need a lot more data to train this model. Now we show some ablation study of RAPIQUE. So in the left figure, we have plotted the feature importance using spatial NSS, temporal NSS, and the CNN features. It may be observed in figure A that only on live VQC dataset that mostly contains mobile videos, adding temporal features incrementally gain performance. But on other spatially dominant datasets like Convin and YouTube, temporal statistics didn't really help a lot. We do observe that there is a significant gain when adding a CNN feature, suggesting that CNN features did provide other information that NSS features cannot capture. And CNN features even benefit more on screen content and gaming videos than on natural videos, as shown in the figure B, which is quite interesting. So we also show the results using different CNN features in the right figure. So the top two CNN are ResNet VGG. They are only trained on ImageNet, while the bottom two with concept and PAC2P, they are fine-tuned on specific picture quality dataset. So this table indicates that we don't really need the features to be, the CNN features to be fine-tuned on any quality task. And we just use a pre-trained backbone on this downscaled frame is already very good for this model, for this RAPIQUE model. So here we show the also an important part, the time complexity comparison. We can say that RAPIQUE is indeed very rapid and also accurate. As we can say, it achieves very good results at a very low complexity. Indeed, RAPIQUE is 20 times faster than the previous state-of-the-art model VDeval, while it achieves even a slightly better performance. So to sum up, we have presented a new blind video quality model called RAPIQUE for efficient UGC video quality prediction. In this model, we propose a new efficient spatial analysis features and temporal analysis features. We are also the first to combine these analysis and CNN features for blind VQA modeling. And the efficient temporal sampling strategy is adopted to further improve this model runtime. And lastly, we have made the implementation of RAPIQUE public on GitHub. Feel free to check these codes. So that's all for this presentation, and thank you very much for your attention. If you have any questions regarding this paper, feel free to drop an email to me. Okay, see you guys. Bye-bye.